But we should have class, right?
I guess I don't know how that slick schedule really works. Um, Thursday, no class. Friday, no class. The school is closed.
Okay, because it's still, like, I checked and it was like I still had all my classes on Thursday.
That's interesting. Yeah, I don't know why it wouldn't automatically cancel that for you.
Because it's usually super accurate.
So we are going to meet on Wednesday, and we're going to meet next week, Monday. Your Unit 3 to 5 test opens on Thursday morning, and it runs all the way until, do you guys know what day the Unit 3 to 5 test closes? It closes Monday night. That is an exception from most of the unit tests, right? Typically, our unit tests are going to run Thursday to Sunday night. Why did I extend it to Monday? Because when I got this email from one of your online classmates, and they said, I thought I was going to get a chance to catch up over fall break and be a person and have a life. And I said, sorry. Then I realized when I scheduled your midterm exam, that Friday of the midterm week was already completely booked, so they offered that I give that extra day the Monday after. So your midterm exam technically runs through the next Monday, which is longer than expected. So I thought I would give you an opportunity on the Unit 3 to 5 test to have it run an extra day longer as well, in case that's helpful. Here's what I'm worried about with extending due dates. If you're anything like me, you're not scheduling it right now. You don't have a plan already. So when it comes to be this weekend and you open Canvas and you go, oh, right, I have a unit test to take, you're just going to take it Monday night. You're going to take it the latest you possibly can, which means Monday in class, you haven't taken the unit test. You're not here to review for the midterm because you don't even have questions from the unit test to ask. I would rather you guys take the unit test before Monday so that you can come in and get clarifying answers before the midterm. And how many of you have scheduled your midterm already? Ooh, that is not enough hands. If you have not, what is the risk in not scheduling it already? Getting a bad time or not getting a time that fits into your schedule at all, right? Are you going to have to skip class just so that you can go take this midterm that has been available to schedule for several weeks? I hope you don't have to. So honestly, like pull it up now and do it if you want to. Ignore my class for a minute while you get that scheduled, because it is pretty important to have your midterm scheduled. But as a reminder, you can take your midterm the Monday after it says on our schedule. The testing center is closed over the weekend. It would be nice if you could test over the weekend too. I would have loved that, but only weekdays. All right. Anything else we should talk about? Got a busy couple of weeks. Oh, is attendance mandatory next week? No. You don't have to come to class next week because I do not plan on covering new material. Instead, I plan on next week, Monday and Wednesday, being review. So some of you would rather just get the midterm out of the way. You feel confident in the material. You don't really care to show up to class, and you don't need the review. Great. You don't have to come. You can take the midterm Monday and be done with it. Some of you know that you'd actually do better coming to class twice to review, so you should bring questions, not just hope that I'm going to have material, because I don't know what you guys need to review the most. You know what you need to review the most. And you can come Monday, Wednesday, and then take your exam Thursday and get a couple of extra days of review in.
So Monday, Wednesday is specifically for the midterm, not the unit, because the unit.
Well, yeah, it's overarching. The other reason that I don't require attendance next week is some of you have very busy schedules where you can't just go to the testing center whenever you would like to. So I would encourage you to schedule it over this class period. And I know that sucks. That means you're there testing instead of here reviewing with us. But I would say it's better than not being able to get to the testing center. All right. I've got this problem up on the board. Can we determine the polar bonds that are in this molecule? What do we need in order to determine a polar bond? Electronegativity values. Can somebody define electronegativity for me? Raise of hands. Not a textbook definition necessarily, just what it means to you. One more time. Attraction of electrons. So a high electronegativity number pulls electrons, attracts electrons more strongly. Good. Do you guys think of it any other way? Lizzie?
I always think of it like how much they like each other, I guess. Does that make sense?
How much the atoms like each other.
Like how similar they are. Like if they're super similar, they're gonna behave different, but like opposites attract kind of a thing.
Oh, I don't know that there's anything about opposites attract necessarily.
Because if you have one that has really low electronegativity and one that has really high, they're like.
Yeah, but also atoms that have the same electronegativity also, you know.
Yeah, so if they're really similar or they're really different, then they can be friends. But if they're just kind of
No, I don't think so. I think you really can get a spectrum of bonding. So I wouldn't try to break it down into be similar or be different, but don't be anything in between.
Yeah.
You'll find everything. So we need electronegativity differences, or we need electronegativity values, and then we'll find the difference in electronegativity. And we have arbitrarily set a line, correct? If the electronegativity difference is 0.4 or less, then the bond is polar. Those atoms share the the bond is nonpolar. Those atoms share the electrons equally enough. So can anybody point out a nonpolar bond in this molecule, acetic acid at the top? C to C, nonpolar. In fact, better than just nonpolar, the C to C bond is pure nonpolar. No difference in electronegativity. Can you give me another one? Do you still feel like you need the electronegativity values in order to do this? Carbon to oxygen is not nonpolar. The carbon to hydrogen is nonpolar. In fact, the difference in electronegativity here is 0.4, and that's the cutoff for being polar or nonpolar. And I think that's intentional. I've never actually seen a textbook say that they decided to do that. But that seems intentional to me, that they said, well, the CH bond pretty common throughout all of organic chemistry, and we're just going to say it's nonpolar. That just kind of creates a behavior of bonds similar to CH, nonpolar bonds. If you need electronegativity values, put them on your cheat sheet for the midterm next week. Print out a form that you can use on your unit test this weekend, and then get a feel for the electronegativity values you really are going to need. Don't put every atom's electronegativity on your cheat sheet next week. By the way, with cheat sheets, I would recommend building a draft of it at least a week before you go in to take your midterm. And then rebuilding that draft at least 2 days before you go in for your midterm. And then revise it again, maybe the night before your midterm. If the more you revise and rebuild your cheat sheet, the less you're going to need it. That's the whole point. Remember what I called it on the first day? It's not a cheat sheet, but a risk sheet. It's a huge risk to bring that sheet in with you if you made it the morning of or the night before. If you don't know how it's organized, you don't know what's on it, it's not going to help you. Okay, these are nonpolar covalent bonds. Are there any polar covalent bonds? Ashley, you're nodding your head. What do you see? Everything else. C to O double bond, polar. C to O single bond, polar. And O to H, polar. This molecule is composed of both polar bonds and nonpolar bonds. Where we're going today is looking at polar molecules. We're going to look at molecules that have polarity overarching, not just within the bonds, but at the molecule at large. Okay, what about this molecule, sulfur hexafluoride? Does that have polar bonds? For this one, I'll give you their electronegativity values so that you can make this calculation. Cole, you're nodding your head. Polar bonds? Yeah. There's a difference there of 1.5, definitely greater than 0.4, and it's less than 1.9. That's our cutoff for ionic bonding. So, polar bonds, good. What about an HCN? Oh, by the way, you didn't need to draw out that structure, sulfur hexafluoride, did you? We just knew that the only bonds there are S to F. What about HCN? Good. H to C, nonpolar. C to N, polar. Just barely. A difference of 0.5 in electronegativity. So this contains both nonpolar bonding and polar bonding. And again, we did that without drawing the structure, but the next thing that we're going to do, we almost always need to draw out the structure. If bond polarity is an unequal distribution of electrons between two atoms, molecular polarity is an unequal distribution of electrons across a molecule. Unequal electron distribution across the molecule. There's a new term that we introduce here, and it's called a dipole moment. You can kind of see the relation here between dipole and polarity. You actually can have more than just two poles. There are instruments. We have an instrument upstairs that is a quadrupole instrument. It's got 4 regions, two that are plus, 2 that are minus. But a dipole moment is talking about this unequal distribution, a place that's more positive and a place that's more negative. We represent a dipole moment with this arrow. This arrow points in one direction, and then close to the butt end of the arrow, you get this cross. Now, you might be able to guess what that dipole arrow is saying if you haven't read up on it already. But the biggest clue to me in the dipole arrow is actually that cross on the left-hand side, because it looks like a positive sign. The dipole moment shows how electron density is skewed. It shows how the unequal distribution is laid out. This is where the electrons are found more often. This is where the electrons are being pulled away from. This symbol up here is little sigma. And it looks kind of like an S, or a little bit like a music note, if you will. You guys can oh, I'm sorry. Not sigma. Glad I had that cheat sheet there. delta positive, delta negative. It's on the bottom right of those green sheets, delta, small delta. As soon as I started saying it, I would have caught it, but not soon enough. So we call this delta positive, delta negative, or partial positive, partial negative. We're using it to say that's not a formal charge. It's not a negative charge on an atom. It's not a negative charge on a compound. It's not a negative charge in a bond. It's just a region where it's more positive than negative, correct? So let's say that I want to do a race. I want to see who can run around our building the quickest. I pair up against Caden, and Caden's faster than me. And then we both run against Usain Bolt. Who's going to win? Usain Bolt. But comparatively, neither of us are Usain Bolt. Neither of us are actually fast. But comparatively, Caden is more fast and I'm more slow. Yeah? This is the idea. Ionic charges are true positive, true negatives. Formal charges, true positive, true negatives. But in the absence of formal charge, you can have this, well, more positive than not, more positive than me, more negative than me. That's what our partial positives are trying to say. So that's what we get in these bonds. If we were to apply these dipole moments to acetic acid, we don't have any dipole moment to show here. Okay, but we actually do, because there is a difference in electronegativity, right? But we're not going to show it. But we could show a dipole moment here. Which way would the arrow point in this C to O double bond? Towards the oxygen. Now, I don't have to use a dipole arrow. I could also just use my partial charges. What partial charges would I place? Actually, let's do the O to H bond. What partial charges would I place on the atoms in the O to H bond? On hydrogen, I place partial positive. And on oxygen, I place the partial negative. Two different ways that we show the dipole at the same time. Okay. Good. Because, like you said earlier, electronegativity is that pull on electrons, right? So what atom is going to have the electrons more often is the atom that is more negative more often because of the electrons. Exactly. Okay, so we get these dipole moments within bonds, right? When you have an uneven, or sorry, when you have asymmetry in the molecule, you get this molecular dipole. Asymmetry with polar bonds creates a molecular dipole. Asymmetry can feel a little vague. You know, there is a chemistry class, inorganic chemistry, where you spend the first 2 or 3 weeks just learning about symmetry. You give different names to different types of symmetries. You learn about different ways you can rotate things to show their symmetry. Symmetry is an incredibly important concept in chemistry. So I'm going to give you guys some examples of what symmetry is and what symmetry isn't. But here's a shortcut to look for symmetry. You know what's wrong with shortcuts, right? Sometimes they bite you in the butt. So you got to be careful with this shortcut. We'll show some examples of when they don't really work. If you have any lone pairs on a central atom, or, I really should say and or, polar and nonpolar bonds to the central atom. There, you're going to lose symmetry in the molecule. If you have both a polar bond and a nonpolar bond, those are different bond types, so they wouldn't be able to be symmetric to each other. And if there's a lone pair somewhere in the molecule, then there's going to be this unequal distribution of where electrons are found. You're going to lose some sort of symmetry in that. And so these are two very good shortcuts to try and pin down quickly, is the compound polar or nonpolar? But the best process for determining molecular polarity is to know the molecular geometry. You have to know the molecular geometry. So when we had acetic acid over there, we already showed the molecular geometry to some extent. For instance, I showed that the C to O to H bond is bent. That oxygen as a central atom is a bent central atom. It's not linear. It's bent. And I already showed that the carbon in the CO double bond is in a trigonal planar geometry. It's not T-shaped. It's not tetrahedral. It's not trigonal pyramidal. It's trigonal planar. Okay, well, notice how this central atom here has two different bond types. It has both a polar bond, and a nonpolar bond. That makes me think that that's definitely going to be contributing to polarity. And here, I have a central atom that has lone pairs on it. That can contribute to molecular polarity. And we already recognized that these were the two polar bonds. So the way that this molecule behaves in terms of molecular polarity, it's got, you might say it's got two different molecular dipoles. This molecule, as a three-dimensional structure, can also rotate around, in which case those two molecular dipoles can actually line up. If you were to set these molecules, several of these molecules next to each other, they'd have some interactions between their partial positives and partial negative regions. Let's look at SF6, though. Sulfur hexafluoride. If we drew this one out, we find that the sulfur expands its octet. So do you think there's any lack in symmetry in this compound? Every bond is polar. I'm sorry, I want to take a step back. Acetic acid is a polar molecule. Every bond in sulfur hexafluoride is polar, correct? So does that make you think the molecule must be polar? If every bond is polar, how can the molecule not be polar? They all cancel each other out. It's completely symmetric, the polar bonds in the structure. This is a three-dimensional shape. In fact, it's a three-dimensional shape that looks fairly spherical. And everywhere around that sphere is the same dipole. It's all this partial negative sitting at the fluorine, which means no one region of that sphere is more negative than another region of that sphere. This doesn't behave quite like a magnet where you've got a north face and a south face and you can align them. It's more like a magnet that's all just north, and it's only ever going to be attracted to south. It's not like this, where it has both a partial positive region and a partial negative region. To be fair, there is a partial positive region of the molecule. It's locked on the inside of this structure. So another molecule that comes up next to it will never interact with that partial positive region. So this molecule, polar or non-polar molecule? Non-polar. There is no asymmetry. There is complete symmetry in this molecule. All right, let's look at HCN. We draw out this structure. We get a carbon-nitrogen triple bond, a lone pair on the carbon, a lone pair on the nitrogen, and a CH single bond. Polar molecule or non-polar molecule? Why don't you guys sketch this out and draw the dipole, the molecular dipole that you think this molecule would experience. Talk with one another as you draw this out and see if you guys can agree that it's a polar molecule or a non-polar molecule. Show it with its dipole. So you see some symmetry then. Yeah. Like if you cut a line of symmetry through the C, the H on the left is definitely symmetric to the N on the right. Oh, huh, okay. H and N, I don't know. Do those look symmetric to each other? A 1 proton nucleus, a 7 proton nucleus? Oh, oh, okay. Why do you sketch that? Here are the next two I want to do. So when you feel ready on HCN, tell me whether SO2 and CO2 are polar compounds or non-polar compounds. If you feel really confident on how to draw these, ask your classmates if they feel confident. Because if you can teach them how to draw them out, it's only going to ingrain it in your head better. remember that this whole section on molecular polarity hinges on being able to draw a Lewis dot structure. That's the skill that has to become second nature sooner than later, because this type of question, SO2, polar or nonpolar, is the question you'll see on the unit test, is a question you'll see on the midterm, and it requires previous knowledge. It requires building a structure. Although, if you were to think about it, because it does in actuality, it's a very small partial charge compared to this, which is not as small. So there's still no symmetry inside of the molecule. They still like separate each other. Yeah, you can do the explanations, whatever. Maybe that'll probably help before we go, but you can finish the before the final. Okay, just a raise of hands. Who has finished drawing SO2? Just drawing its structure. Okay. Yeah, I think you, no, it's not the right Lewis structure though. You don't have an octet as sulfur. Right, what you got? Question. Question.
Oh.
Do you feel like it follows one of these shortcuts?
It definitely does.
Which one?
Well, it's got one parallel to central.
Yeah.
But what if?
What if indeed? What you got, Carter? Good. Oh, you can. Your structure here is it's not this easy. You've got an expanded octet at oxygen. Oxygen can't expand its octet. Which of those atoms can?
Wait, at all. Oxygen. Because isn't it the opposite expand?
Yeah, and oxygen's a two.
Am I stupid?
So you have third
Oh,
here,
I
and you need
I
those
thought oxygen
electrons.
was three down.
Great. Yep. Did you use the shortcut at all?
Yeah.
Good. Great job. We're determining if these two compounds are polar or not. And the first thing you have to do, Saint, is draw their structure to determine.
Thank you.
You have 3 there. missing 2 electrons too in this structure. If that solver really was just double bonded to the 2 lows, 2 electron regions, linear. But you used these 2 and these 2 for a double bond, these 2 and these 2 for a double bond. You got these lone pairs, these lone pairs, and this lone pair on the sulfur. So you're missing 2 electrons.
So that one missing.
Yeah, and that's why it takes that shape.
Oh, okay.
Yep.
So it's not.
It's not a it is good. Yep. Because you call it polar. These arrows just say there's a negative region here, positive region here, negative region here, positive region here. The way it's wrong is you agree there's some symmetry. Negative, negative. Yeah. Right? But actually, this sulfur is wrong.
Yeah.
Because this sulfur has 1, 2, 3 electrons.
I think how extensive
So horrible. So far over his head.
All right, you guys ready? With hydrogen cyanide, HCN, we have one central atom, the C, and it has what type of electron geometry? Carbon has what electron geometry here? Linear. So if we're looking for symmetry, it's kind of easy to look for symmetry. I just cut right through it and look at the 2 linear sides, right? H does not reflect into N. They don't have the same electronegativity values, which means that this molecule lacks symmetry and it has polar bonds. The only polar bond here is C to N. So this is the bond dipole. It's also the molecular dipole because it's the only bond dipole present. Remember, I came back in, I sketched out all of the bond dipoles in sulfur hexafluoride, and you can kind of see how they cancel each other out. Like these 2 fluorines, they pull exactly opposite of each other. These 2 fluorines exactly opposite. These 2 fluorines exactly opposite. Do you know what the electron geometry is at sulfur? Octahedral, 8-sided face. And remember, those more obscure geometry names, the ones you feel less familiar with, those are the ones you really want to study or take up some space on your cheat sheet with, but know how you're taking up space with them. Its electron geometry is octahedral. Its molecular geometry? Also octahedral. That means it's got that symmetry. and it doesn't have any lone pairs on the central atom.
So if its molecular geometry and its electron are different,
If molecular and electron geometry are different,
then you're gonna have
that means you've got a lone pair on your central atom, and that's almost always a clue towards molecular dipoles. Okay, so we said this compound was nonpolar. I want to take a step back because I just mentioned that these dipoles, they all have a counter effect on each other. And I wonder if any of you are looking back at acetic acid saying, don't those two dipoles have a counter effect on each other? They're pointing opposite, right? But they're not really pointing exactly opposite. They are offset from each other. If they were pointing exactly opposite from the same central atom, I would agree with you. They offset each other. But they're actually pointing opposite on different central atoms. Would you guys agree? Huh?
I can just imagine it, like, if you imagine the movement keep going.
Yeah.
Spin.
All right, so hydrogen cyanide, it has polar and nonpolar bonds. This is a polar molecule. SO2. When you were sketching these out, you needed to count all the valence electrons. You needed to place the least electronegative in the center. And you needed to follow the rules of resonance. You needed to minimize charge, maximize octets, place charges on the most relevant atom, the most appropriate atom. This is the Lewis structure that most of you most likely got. Now again, using this rule, if electron geometry and molecular geometry do not agree, if there is a lone pair on the central atom, that's what this is trying to say. Electron geometry does not agree with the molecular geometry. We've got good reason to believe that this compound is polar. Although when you look at this and you do this same like canceling out thing, you draw it like this, boy, it sure looks like they cancel each other out, right? That's not its shape. It's not a linear structure. It's got a trigonal planar electron geometry and a bent molecular geometry. Now draw in those dipoles again. And you can see that they don't cancel each other out. They actually point in the net same direction. So you can think of polar bonds being kind of like puller. And if these pulling forces sum together in any way, then you're going to have a net molecular dipole. So imagine that the S is a cart and the two O's are horses pulling on them. One is trying to pull to the right, one is trying to pull to the left, but together they're going to pull it straight forward. The molecular dipole here looks like this. They sum together down the middle. But our shortcut, we didn't even need to look at the geometries. We recognized that sulfur had a lone pair on the central atom. That's going to ruin some of the symmetry, especially with the fact that we have polar bonds. S to O is a polar bond. With polar bonds, lone pair on the central atom, SO2, polar molecule. Can I answer questions on that one? CO2. Here, we get two double bonds to the oxygens on either side. True or false, this compound has polar bonds. True. This compound has polar bonds. Those polar bonds point towards the O. So again, we're looking for asymmetry in a molecule with polar bonds. Is there asymmetry here? Is there a lone pair on the central atom that would change the molecular geometry from the electron? No, electron geometry linear, molecular geometry linear. And I don't have polar and nonpolar bonds. I have only polar bonds, which means these polar bonds, oriented directly opposite each other, completely cancel out. All right, I want to do one more example with you guys. This is a compound called chloroform, trichloromethane. You guys all know what chloroform is used for in the movies, but in the organic chemistry lab, chloroform is a very common organic solvent. The structure that you would get for chloroform looks like this. I mean, the hydrogen could have gone to any of those positions. Does this compound have polar bonds? What are the polar bonds? C to Cl is polar. Okay. Are there any lone pairs on the central atom? No. Are there polar and nonpolar bonds? Yes. So this compound is polar. There is a lack of symmetry at some point because of this hydrogen. The chlorines aren't always going to be symmetric. If we draw this structure with its true geometry, its tetrahedral geometry, I can actually sketch out for you a plane that shows that they're not symmetric. Right here, my two chlorines reflect into each other, but my hydrogen and my chlorine do not. Which means all of these bonds are pulling towards the chlorine, and there's a net molecular dipole that puts a partial positive by the H and a partial negative underneath all three of the chlorines. Okay, one last one real quick. Natural gas, methane. I'm sorry, I realize I haven't been keeping up on analyzing these. CO2 we said was non-polar, despite having polar bonds. It has symmetry. Chloroform, polar. Methane, polar or non-polar? Does it have polar bonds? Okay. If it doesn't have polar bonds, how can the compound have a molecular dipole? The molecular dipole is a summation of all of the individual bond dipoles. So if there is no bond dipole, there cannot be a molecular dipole. So step one, when determining molecular polarity, are there polar bonds? Yes or no? Is there a lone pair on the central atom? Yes or no? And are there polar and nonpolar bonds? Those are kind of the three ways to go through it. You didn't even have to sketch out CH4. All you had to recognize was that there cannot be a polar bond in CH4. All right, what questions do you have on molecular polarity? There are some exceptions, as always, to my shortcuts, which is if you look back at those MOFs that we were dealing with, if you have like a square planar central atom and it's got a lone pair on top and a lone pair on bottom, technically that means there's lone pairs on the central atom, but those lone pairs are symmetric to each other. So you haven't like lost symmetry there. Or you can have like a linear geometry where you have 4 lone pairs in a square planar configuration. And a linear geometry means you can find symmetry. So there are some exceptions to these. They are less and less common on your like unit and midterm questions. They're out there, but the shortcut works 90% of the time. Yeah? Yeah, I guess like 2 or 4 lone pairs will. Well, then you're kind of looking at, do you still have polar and nonpolar? Do you have different types of bonds that aren't symmetric? Because that can create still a dipole. But sometimes lone pairs on the central atom can still give a nonpolar compound. Less common that you'll see it on your tests, which is why these shortcuts work really well. There was one last thing that I didn't mention in our last section. I don't want to spend a lot of time on it because it's not something you'll see on your test much, but I do think it's interesting. Not all electron regions repel the same. We decided geometry based on VSEPR theory, valence shell electron pair repulsion. It turns out that lone pairs of electrons repel greater than bonding pairs of electrons. And when those bonding pairs of electrons are more dense, they repel greater than bonding pairs of electrons that are less dense. So a lone pair repels other electron regions very strongly. Triple bonds, which have 6 electrons in them, repel other regions strongly. Then double and single bonds repel other electron regions less strongly. Here's a cool application of this. Water, polar or non-polar? Polar, because we've got lone pairs on the central atoms and polar bonds. What is the electron geometry of water? Tetrahedral electron geometry, bent molecular geometry. What bond angle do we expect? What angle of repulsion between electron regions do we expect in tetrahedral electron geometry? Anybody? 102? Not 120. 120 would be a perfect triangle.
Oh, you're right.
Trigonal planar. We expect 109.5, which is a kind of an odd number, right? The others are 180, 120, 90, 109.5. Definitely the exception. We expect to find a bond angle here of 109.5, but we actually find 105 degrees. The 2 hydrogens of water are closer to each other than we expect. Why are the 2 hydrogens closer than we expect? Because these lone pairs are repelling more than we expect. These lone pairs repel each other, and they repel the bonding regions more than the bonding regions can repel each other. If these 2 bonding regions were repelling each other the strongest, then we'd be larger than 109. They'd be pushing each other away to 110, 111, 112. But instead, they're actually being pushed closer to each other because the lone pairs that are up here are pushing them closer. They can't repel each other as much as the lone pairs can repel them. Cool application that shows we can simplify this stuff, but there's unique differences between all these bonding regions. All right, we're going to get into Module 11 next. So I want you guys to take a minute to move around and get your blood flowing. Let's come back in at 11:03 to keep moving. It is sulfur dioxide.
Why do the O's come down?
They're repelled
That's how I wrote it.
by the lone pair. Yep.
Oh.
You can draw a Lewis structure any way you want to because it's kind of just like a drawing, right? in the same way, you can draw the Eiffel Tower any way you want to, but it doesn't need to obey reality, right? Once you draw the Lewis structure, you realize the electron geometry and the molecular geometry, and so you can redraw it to obey reality. Does that make sense?
Yeah, the first time I wrote it, actually, I had the sulfur just double bonded to
One
the
side.
oxygen.
Mhm.
Yeah.
That's actually a valid form, but it leaves a negative charge on O and a positive charge on S. And you're missing a lone pair, actually. There was 2, 4, 6, 8, 10, 12, 14, 16, 18.
Isn't just there 18?
Oh, I do see. You actually have too many electrons on O.
Oh, okay.
You've got a double bond and 3 lone pairs.
Oh,
And
okay.
you're not satisfying the octet with sulfur.
Okay.
So you would actually want a lone pair moved over.
Okay.
I'll clarify that state for you. Okay.
Thank you.
So you could have drawn this,
Yes.
which still would have been bent. It's still a bent molecular geometry. I'll try to draw it as such. But if you calculate the formal charge here, do you remember how to calculate formal charge?
Yeah, you have to find like the electronegativity.
Nope. Valence electrons
Oh.
minus.
Oh, minus the lines and the dots.
Good.
Too.
So why don't you calculate the formal charge on S and the 2 O's, because the 2 O's are different here.
I did 6 minus 2, the non-volatile electrons that you have on top, and then 61.
Oh, but it's what? 2 plus. Yeah, I like to put dots plus lines in parentheses to kind of all they work together.
Okay.
So sulfur has a
Negative
6 minus 5
1. Oh, sorry, positive 1.
positive. And this molecule is neutral overall. So if there's a positive somewhere in the molecule, there must be a
Negative to balance it out.
exactly. Where do you think that negative is?
On the right side?
Yes. This is an oxygen that has 2 bonds and 2 lone pairs. It's happy that way. Look at water, 2 bonds, 2 lone pairs. This actually has too many electrons. One of our rules about resonance forms is that we want to maximize, or we want to minimize charges first. Our first rule is minimize charge.
Right.
So what we'll do is show one of these lone pairs moving to form a double bond with the sulfur. Do I need to be worried about breaking sulfur's octet? No. Sulfur can expand its octet because it's in the 3rd row, and atoms in the 3rd row or lower have access to d orbitals where they can put excess electrons.
Right. Okay.
Notice how I took from the negative and I shared with the positive, and that brought both of them down to neutral.
Okay. That makes sense. Can I take a picture of that?
Please do. So these are resonance forms. This is the major resonance form because it minimizes formal charge.
Okay, that makes much more sense. I just skipped some steps then. I didn't calculate the formal charges.
Yep. Now, oftentimes you're actually gonna you'll get to a pattern and you'll realize I should probably just expand sulfur's octet. Any chance you get to, just expand sulfur's octet. Because that will almost always minimize the formal charges.
And expanding the octet is taking a lone pair and moving it to
Expanding the octet is placing more than just 8 electrons around sulfur.
The lone pairs repel stronger because they have more wiggle room, right? Like they can be out further, so.
And Saint, how many electrons around sulfur here? Is that octet? Yeah, that's like a dectet, right?
Yeah.
Decet. So that's what we mean by expanding. It goes beyond 8.
And it can do that. Sorry, it can do that because you have like the 1s and then the 2s and you come down.
Sulfur is in the 3rd row.
Yeah.
In the 3rd shell, we have 3s,
Yes.
3p, 3d.
Yes.
Okay, to be fair, the 3rd row doesn't actually have the 3d, but the 3rd shell does. The first quantum shell
Yes.
is only s.
Yes.
The second quantum shell is both s and p. Every time you go down a quantum shell, you add a new subshell. The 3rd shell is where we get access to the d orbitals for the first time. But the 4th row also has d and f. The 5th row has d and f and g. Don't worry about it.
Okay. Thank you.
Why do lone pairs repel more? I wouldn't say it's because they have more wiggle room or they take up more space, but bonding pairs of electrons are delocalized around more atoms, so actually they have more space,
Okay.
whereas the lone pairs are a little bit more localized,
They're more compact.
so
I thought it was the opposite.
they're a little bit like less shielded by protons. They're less shielded by nuclei.
Okay.
All right, we are moving into Module 11, and this will wrap up Unit 4 for us. We're talking here about advanced theories in covalent bonding. I think it's funny that they call this advanced theories. No, this is just normal theories. So I don't want you to look at the title of this and think, oh, this is so hard. This is above my pay grade. This isn't something I'm going to be able to. This is too advanced for me. Trust me. By the time you get into organic chemistry, this is an expectation that you understand this. We've been talking about Lewis structure theory and Vesper theory and how they explain the way that the atoms bond to each other or how they're connected to each other and how they take up their space. Lewis theory shows us atomic connection, right? Structure. Actually, I'm going to say not atomic. Molecular structure. Vesper theory. Taught us geometry. Molecular shape, if you will. But it didn't actually talk to us at all about the nature of the bonding. How are those electrons involved in creating bonds? Where are electrons found again? They reside in, I think I might have heard it, orbitals. That's where electrons are. Electrons are in orbitals. And we haven't talked at all about how orbitals are involved in bonding. So we introduce now valence bond theory. Valence bond theory says a bond exists if two things are true. Orbitals of two atoms overlap, and an electron pair fills those orbitals. And it turns out we have different types of bonds that will have different lengths, and we can correlate bond length with bond strength. I think you guys are going to come back and do a lot more of that in Gen Chem 2. But we get this issue. If we were to look at water and start at just the oxygen atom, what orbitals, what valence orbitals are here on oxygen that can be used for bonding? What are oxygen's valence orbitals? Not just p, but give me the quantum shell, the principal quantum number. Is it 1p, 2p, 3p? There is no 1p. And oxygen's not in the third shell. So oxygen has the 2p orbitals, which remember, and don't worry about drawing this if you don't want to, because it's going to get a little cluttered. Remember the 2p orbitals are along the cardinal axes, x, y, and z. But that's not its only orbitals in the quantum in the valence shell. What other orbital in the valence shell does it have? Not s, 2s. And the s orbital is just a sphere. Okay, so there it is, clear as day, all of the orbitals that oxygen has. And I want an overlap with hydrogen's orbitals. Hydrogen valence orbital is 1s. Okay, notice I've got the orbitals to overlap here and here. Great, I've now created covalent bonds between O and the two H's to make water. What is their bond angle? Really? Is that what you think this is? 105 degrees? Looks like 90. Not to mention, you can see that I've used the px and the py. What is the angle between x and y on an axis plane? 90 degrees. We can't use atomic orbitals to explain molecular bonding. It doesn't give us the expected bond angles. So, we get these hybrid orbitals. These come from LaCoA. Honestly, I don't think that you need to expand it. It's not really going to help you very much, but it's linear combination of atomic orbitals. This is math. And what were the atomic orbitals anyways? Math. They were mathematical equations that described the size, shape, orientation. They even had these plus and minus parts of their equation. So we're just going to do new math to the math that we already had to get new math to describe electron orbitals. A couple of things to know about hybrid orbitals. When a sun explodes and it sends out baby atoms for the first time, those are what we call free atoms. And those atoms, very high energy, not involved in bonding, those atoms have your expected atomic orbitals. Hybrid orbitals don't exist there. Hybrid orbitals only exist in molecules, only in bonding. You don't create hybrid orbitals until you have a need for hybrid orbitals. These are not atomic orbitals. They're not S. They're not P. They're new combinations that consume S, P, D orbitals and create new ones. So they have unique shape, unique size, unique orientation. If S is spherical and P is propeller along 3 axes, then the hybrids of these are not spherical, are not propeller, are not necessarily aligned on axes. When you create hybrid orbitals by linearly combining atomic orbitals, you preserve energy. But the reason that we do this comes back to this: electron repulsion. We just showed that if I took atomic oxygen and tried to bond it with hydrogen, the best orbital overlap I can get is 90 degrees. That's going to be a lot of strain. 90 degrees actually pushes those bonding regions closer together than 105. So why does an atom hybridize its orbitals? Why does it create new math to define new regions for its electrons to go? It's all in the effort of minimizing electron strain. Deal? Atomic orbitals like this, they just come from the math. But hybridized orbitals, they actually come from these expected geometries that we want. So, overall, Vesper. Vesper is strongly connected to hybridized orbitals. Okay, I love hybridized orbitals. And it's all right if you don't love it, but you are going to see it. So I hope that I can inspire you a little bit. We're going to look at 3 main types of hybridized orbitals. And these are most common in the second row, but also a lot of the chemistry that you do is second row elements. The first type of hybridized orbital is called an sp orbital. It's not S, it's not P, it's SP. That's the name. I do agree somebody probably could have gotten more creative here, but it is the most descriptive name that it can be. This is the combination when you take the s orbital, fully spherical, with 1 p orbital. So I'm going to show you guys a reminder. This is where s laid, and this is where the 3 p's laid. And we're going to take just s and p. This is like taking the sphere and the propeller. I'm actually going to, it doesn't matter which one I choose. I'm going to choose the px that's laying down. And I'm going to combine these, which means I'm going to overlay them. So I could actually draw it like this. Yeah? Shaded means a negative sign in the front of the math equation. Unshaded means a positive sign in the front of the math equation. We say that's being in phase or out of phase if the shadings line up. You can see that the s orbital is in phase with half of the p orbital, and it's out of phase with half of the p orbital. That's going to lead to constructive interference and destructive interference, and I get a shape that looks like this. Right? You see it. The unshaded regions are in phase, they expand. And then the left-hand side, there's the unshaded part of the S and the shaded part of the P, they subtract from each other. That orbital, does it look S? I mean, a little bit. It's got one really large lobe. Does it look P? I mean, a little bit. It's got two lobes. But it's not S and it's not P. It's an orbital that exists as the combination of both of them. Here's another tip. The number of orbitals that go into hybridization is equal to the number of orbitals that come out. So if I get one orbital that's oriented this way, I get an equal and opposite orbital oriented the other way. And then there's another piece I want you to recognize about this. I have three p orbitals, px, py, pz. Which p orbital did I take? Px. So the new orbitals that come out of this can only have orientation along the x-axis. These are linearly aligned with each other. In terms of the orbitals, when I get on the other side, I have two p orbitals that have not changed. And right at the middle of S and P energy, I get two orbitals that are now sp. Here's how this connects back to Vesper. If you have a linear geometry from your central atom, then your atom is sp hybridized. Absolutely. We actually were just dealing with an sp hybridized compound earlier. That carbon in hydrogen cyanide is sp hybridized. It has a linear geometry between H and N. In order to get a linear geometry, it needs to have two sp orbitals that are aligned linear to each other. There's another compound we had up on the board earlier. Carbon dioxide. sp hybridized at that central carbon. Linear geometry, sp hybridized. These work both ways. If you can draw a structure and determine its electron geometry, then you know it's hybridization. And if you know it's hybridization, you know it's electron geometry. Plain as day. How do you guys feel about that? New orbitals. Did you think you were done with orbitals? We're just getting started. All right. The question I hope you're asking now is, what's next? Why stop with hybridizing S with just one p orbital? Why don't I hybridize S with two p orbitals? Notice where the 2 is. It's not a subscript. It's what? It's a superscript. That is written intentionally. That's something that you guys need to get familiar with. sp2 orbitals These come from the combination of S with P and another P.
So then the little thing
Clear as day.
is this.
How many orbitals are coming into the hybridization? S, P, P. So how many orbitals should I get out? sp2, sp2, sp2. If we're starting, again, with S and P here, I'm taking the S orbital and 2 of the P's, and I'm hybridizing them. That means that there is a p orbital on the atom, an atomic p orbital, the ones that we talked about earlier, that remains exactly as the math describes it. But now, 2/3 of the way towards p, I get 3 new orbitals. Yeah, because I've got 2 orbitals of the same energy, 1 orbital of a lower energy. I averaged them out. This is a little bit beyond halfway between them. And these 3 orbitals are called sp2. When you take the s orbital, the px and the py, you're no longer constrained to just one geometry or one axis, right? How many axes do you have now? 2. You get px and py. That defines what? It defines a plane. X and y is a plane. So the furthest these 3 orbitals can spread out in a plane looks like this. These are my sp2 orbitals. I want you to notice they look a little bit more like P than the sp did. I mean, I'm combining more P than I did last time, so it should look more P. These are all just math equations that we're just combining together. But now I have orientation along the xy plane, and I have these 3 orbitals. Those are going to define a plane, and they want to minimize energy. They want to minimize electron strain, so they're going to spread out as much as they can. What geometry aligns with sp2 hybridization? Trigonoplanar is sp2 hybridized. Lizzie?
So we know that there's 3, but like when you're just looking at the what values you have for the orbitals, why isn't there 4? And when you're doing 3, like it's they want to spread out, so that's why you use the shape. But like looking, that doesn't make any sense to you, does it?
I'm a little confused.
Okay, so like on the just the SP, knowing we had just the S and then just the PX, we were able to be like, oh yeah, we know we're gonna have one on this side and one on this side.
Yeah, because there's only one axis, px.
Yeah. So
But now I have
2x,
axis,
why
px
is it
and
not-
py. But why is it not linear and then straight across? Because they're working to minimize their electron strain. So these orbitals are trying to spread out as much as they can. Remember, being at 90-degree angles wasn't helpful before. Now that they've combined the px orbital and the py orbital, they can spread out across that entire plane as far as they want to. Trigonoplanar is being spread out as much as they can.
I meant like, why do we, like, I know we put 3 in so we get 3 out, but like, why isn't it 4 is what I mean.
Because you put 3 in. So you get 3 out. I don't, like you put 2 in here, we got 2 new orbitals out. I put 3 old orbitals in here, I get 3 new orbitals out.
So it doesn't matter that, okay.
Let's look at the last combination, which is going to be called what? sp3. I'm not even going to try to draw this because you can see it just gets unhelpful. But when I combine S with px, py, pz, I now have access to not just one dimension, like linear, not just two dimensions, like trigonal planar, but I have access to all three dimensions. So my orbitals actually take on this shape. What shape is that? Tetrahedral. It's a three-dimensional shape. And if you wanted to try and draw the orbitals, they look something like this, where the one coming towards you kind of hides the back, and the one going away from you kind of hides the front. Not easy to interpret, but they spread out in they spread out in three dimensions. And when you look at what happens with the hybridization, S and P, all three of the p orbitals are being linearly combined, mathematically combined with the s orbital, and so none of the orbitals lie at the old energy levels. Instead, all four of the energies lie at a new energy level, an energy level that is 3/4 of the way towards P. It's a little bit under P because I'm hybridizing them with S, but it's closer to P than S. And what geometry aligns with sp3 hybridization? Tetrahedral. This is something you may see on real chem more often, but something you will see less on your unit test. And that is that in row 3 and lower, you can get d orbitals. Obviously, row 2 doesn't have d orbitals to combine, but sulfur can do something like sp3d, sp3d2. These are covalent bonds, yes, not ionic bonds. An ion has no reason for this hybridization, because an ion isn't trying to minimize electron strain. This is just covalent bonding. Okay, let's apply it. In fact, I don't know if you still have your compounds from last time, but you could go through this and try to define the hybridization everywhere. But I'm going to draw a few compounds up, and I would like you guys to determine their hybridization. Actually, I think I'd rather go through this as a class, so we can spend a little bit more time on it. BF3, raise of hands. Hybridization of BF3, right? sp2? Tell me how you got there. How did you know it was a trigonal planar shape again? Three electron domains, 3 electron regions. And here's a tip. 3 electron domains, you can just count up. S, okay, I ran out of S. P, P. Okay, I got through 2 P's to count to 3. sp2. But the way that you ran it, which was, I have 3 electron domains, they spread each other out into a trigonal planar, and being trigonal planar is being sp2. Boron here is sp2 hybridized. I think counting shortcuts a little bit, so you don't have to work through the electron geometry, but it's never a bad time to practice electron geometries. Who wants to give me the carbon here in dichloromethane? Can I call on Berkeley to give it to me? Yeah? How'd you get there? Tetrahedral, because it's got 4 electron regions. Tetrahedral electron geometry. Tetrahedral takes up 3D space, needs all 3 of the p orbitals. But again, we could have counted there by saying 1, 2, 3, 4, SPPP, SP3. Do you guys get what I'm saying when I'm counting up to it? All right. Who wants to give me the oxygen in acetic acid? Blake? Yeah? Which way are you using to get there?
Has 4 domains, so it's
4 domains, tetrahedral, sp3 hybridized. What about the carbon double bonded to O? Raise of hands. Lizzie? How did you get there? Three electron domains, trigonal planar, SPP. SPP is sp2. Cole, you want to give me the sulfur in sulfuric acid? sp3. 4 electron regions, SPPP. And who wants to give me the oxygen bonded in the OH of sulfuric acid? There is some assumed character here that I haven't drawn out. There's 2 electron pairs on that oxygen. I just haven't shown them. Oh, it's definitely bonded to the H, and it's bonded to the S, and it has 2 electron regions. We would expect sp3. Good. Okay. Yeah. Because if you go, okay, so you remember how there are actually larger electron geometries that match up again with the molecular geometry? We're not looking at molecular geometry here. Actually, we are in each of these cases because there's no lone pairs on the central atom. But we're actually using electron geometry. Let's look back at sulfur dioxide. And let's look back at sulfur hexafluoride. How many electron regions around sulfur in sulfur dioxide? 3 electron regions. So the hybridization, sp2. And its electron geometry is trigonal planar. So we're using electron geometry. If we were trying to consider molecular geometry, we would have said 2 electron regions. That would have made it sp, but an sp hybridized atom is linear, not trigonal planar. So we have to use electron geometry. Does that make sense? And so in that way, yes, linear electron geometry is sp. Trigonal planar electron geometry is sp2. Tetrahedral electron geometry is sp3. Even the molecular geometry subsets, tetrahedral, trigonal pyramidal, bent, those are all tetrahedral electron geometry, all sp2. What about sulfur and sulfur hexafluoride? How many electron regions? 6. So sp3 doesn't get me to 6. That's s and 3p orbitals. That's only 4 orbitals to combine. I would also need d2. So sulfur, phosphorus, most of your halogens, they can expand beyond sp3 hybridization.
I think you were describing like the p orbitals described the x, y, and z on the plane. Is d the same, or is that going to like fourth dimension or something?
No, it doesn't get into the 4th dimension. It actually, there's 5 d orbitals. Some do lie along planes, some lie in between planes. So it's more about hybridizing in a way that allows sulfur to reach in 6 different directions at the same time, whereas tetrahedral only allows sulfur to reach in 4 different directions at the same time. Yeah?
And D can have 5, right? Because they hold 2 each.
There are 5 d orbitals.
Yeah.
The d subshell holds 10 total electrons.
So like,
But I don't think you'll ever find an atom that's hybridized sp3d5. That's a lot of electron domains. In theory, you could get there, but I think in practice, that compound would be very energetically strained. All right, to wrap up Module 11, we're actually going to name some of these bonds that result from specific overlaps of orbitals. Now there's your lowercase sigma. That's more like an O with a hat on. You can see it in the middle right of those green letters is sigma. We're going to name some bonds sigma and some bonds pi. You go far enough in chemistry, you'll learn about delta bonds as well. And there is a connection here. Sigma starts with S, pi starts with P, and these kind of hint towards what types of orbitals are allowed to create these types of bonds. First of all, a bond will occur if the orbitals are in phase with each other. We were looking at the definition of a bond. The definition is that the orbitals overlap. But it's not just overlapping in any way, it's when the orbitals overlap in phase. So if we're going to look at H2O, and I want to zoom in on the OH bond. What is the hybridization of O in H2O? Look back in your notes. We had it drawn out. How many electron regions? 2 bonding, 2 non-bonding, sp3. So oxygen here has an sp3 hybridized orbital. And we're trying to overlap that with hydrogen's orbital. What orbital does hydrogen have? S. So we're trying to show this overlap. This is in phase. The non-shaded and the non-shaded overlap. And we actually get something called an antibond if it overlaps like this, where H is shaded and the part it's overlapping with on sp3 is unshaded. A bond only occurs when the orbitals are overlapped in phase, not out of phase. Okay, so there's a lot of combinations I can have. For instance, I could have an S to S overlap. I can have an S to SP overlap. And I can go on S to SP2, S to SP3. I could also have an SP to SP overlap, where these regions of sp orbitals overlap with each other. And in the same way, I could go on. I could have sp to sp2. I could have sp to sp3. In a less common occurrence, I can also have a hybridized orbital overlap with a normal p orbital. So this is sp to p, where again, the unshaded regions are overlapping. But what's more common with p orbitals, I think, you know what, I'll show this other, a little bit less common. This is where p overlaps with p. We call this head-on, when the tops of the orbitals are all pointing into each other. What's more common for a p orbital to do it's more common for p orbitals to bond side-on, side to side. Okay, so the rigorous definition is that a sigma bond looks like an s orbital when viewed through the bond. Of course. The shortcut is that a sigma bond is a head-on overlap. So if I look again at this s orbital to sp3 orbital overlap that we see in water, how do I sight down the bond? Am I sighting down the bond by looking at the board? I'm looking at the bond. I'm not looking through the bond. I would need to take my perspective and set it in the plane of the board, correct? So I can actually model that by using this. What's that? It's an eyeball. And I'm going to look through this. And what do I see? It just looks like an s orbital, doesn't it? Because it's blocked. Exactly. I put my head here, and all I see is this big round orbital at the front. Head-on overlaps look like s orbitals, so we call it sigma bond. A pi bond is a side-on overlap. And it looks like what? Looks like a p orbital. So again, I'll draw this side-to-side overlap of p. I'll put my perspective in the plane of the board, and I'll look through this. I'm looking at the bond right now, but as I look in through the plane of the board, all I see is that front orbital. What does it look like? It just looks like a p orbital. Here's the deal about how sigma and pi bonds show up. Every bond has one sigma bond. When atoms bond with each other, they sigma bond first. No more, no less than one sigma bond. Each additional bond is pi. Here's a quick compound. Formaldehyde. How many sigma bonds in formaldehyde? There's 3 bonding regions, correct? And every bonding region has one sigma bond. This is sigma, and this has sigma plus 1 pi. There's a sigma bond overlapping C and O, and there's a pi bond connecting C and O. Here's a compound, carbon monoxide. How many sigma bonds in carbon monoxide? Just one, because every bond, every time atoms are bonded, has just one sigma bond. So this has sigma. What are the other 2 bonds holding carbon and oxygen together? Pi. Sigma, pi, and pi. Without fail, that's how atoms bond. Each bond starts with sigma. Each multiple bond just goes on with additional pi. True or false? It is possible for a compound to have 0 sigma bonds. False. If a compound has atoms bonded together, it must have sigma bonds. True or false? It is possible for a compound to have 0 pi bonds. Very true. All right, we're done with Unit 4. Wednesday is Unit 5. Bring your calculators Wednesday. We're going to do a lot of math, all right? Have a good day. Go do your homework, and I'll see you guys on Wednesday. Thank you for your time.